All right, so here's the notes on 6.2c, which is also technically the review lesson. You should have already watched the video where we filled in the table, and I want to just remind you that transforming means we are doing a constant multiplied or added or divided or whatever times a random variable to get a new random variable. When that happens, you get the mean of y is a plus b mean of x, and standard deviation of y is absolute value of b, standard deviation of x. These are the formulas we did in 6.2a, and they should also be on your formula sheet, but I just want to have them in front of me for this lesson. Combining is when you're adding two separate random things, and we did that in 6.2b. So mu x plus y would be mu x plus mu y. The mean of the sum is the sum of the means. The mean of the difference is the difference of the means. Standard deviations do not add or subtract, but variances do. So if you want the standard deviation of x plus y, what you do is you add the variances and then square root it to get the standard deviation. And that's the one that looks like the Pythagorean theorem. And I call it the Pythagorean theorem of statistics because it is. Oops, that's a minus. Let me write it again so that it's neat. Sorry, this is a minus, but this is a plus. And it's supposed to be, it's not a typo. Sometimes people look at it and say, oh no, you made a mistake, Mrs. Crum. No, I didn't. It really does add. I have one more reason why it adds that I'd like to tell you as part of these notes, and then we're going to do an example of using these because that's what was missing from the ice cream and cake. You had some examples where you just tried it with very small numbers. We're going to see what this is good for today. So this is, let me finish writing what I was just thinking of. This is the Pythagorean theorem, statistics version. If you did the optional slides from the ice cream and cake, you found out that this whole thing only works if they are independent. If x and y are independent, there are other formulas for when they're dependent that we're not even going to learn this year. All of that only works if they're independent. If they're dependent, like we saw on those optional 2 slides, the formulas just don't work and other things happen, and we're not going to worry about that. But what I would like to talk about before we do the big example is why do variances add when you're subtracting? That's weird. Let's talk about that. Why? I mean, one of the reasons why is what you found out in the ice cream and cake worksheet, or not worksheet. This year it's not a worksheet, it's a Desmos thing. It's a weird thing and it's hard for people to understand, but I have another way of understanding it that might help you. So let me just say, when subtracting random variables, why do you get a bigger spread? And for this, we're going to talk about cereal. Because this is a way to help people understand it. You could do it with the cake and taking a bite out of the cake, but I'd rather do something different. So we have a box of cereal. Really amazing artwork here. And the box says 16 ounces. Now that you've had some experience with statistics, do you think that every single box of whatever kind of cereal it is has exactly, precisely 16 ounces in it? No, I hope you said no. No, of course it doesn't have exactly 16 ounces. It has approximately 16 ounces. And most of the time, because it's a measurement error, it's going to follow a normal distribution. If you took all cereal boxes and measured exactly how many ounces, they'd cluster around 16 ounces in the middle, but they'd have some kind of variation to them. And some would be above the mean and some would be below the mean. And the company hopes that you won't measure the ones that are below the mean because you might sue them. That would be bad. So it's approximately 16 ounces. And so we have a certain amount of variation here. I take my cereal and I pour some into a bowl. Once again, amazing artwork. I pour a bowl of cereal. And let's say the serving size listed on the box is 2 ounces. So this cereal box now has 2 ounces less of cereal than it did before. Got it? Well, actually, that's a lot of cereal there. I end up with a box with slightly less. Let's see if I can, if this box looks bigger, which is not what I meant. So this cereal box has less cereal in it than the other one. This is the remaining cereal. And we're going to talk about what happens with that. So now that you've admired my amazing artwork, do you think that every single time you pour a bowl of cereal, you're going to get exactly 2 ounces of cereal in that bowl? Please say no. In fact, this one probably has even more variation than that one because this is based on a machine. This is based on human error. So I'm going to make a slightly wider normal curve maybe for that and say it has 2 ounces in the middle. But some people are going to pour more. Some people are going to pour less. It may or may not even be normally distributed. But yeah, there's some variation there also. So when you do this, you have some variation, you pour a bowl, and now you have this variation also, and what's left is a combination of these two variations. What's left is approximately 14 ounces, but I'm making this wider on purpose because that variation is not going to be less because you poured a bowl. It would be less if you had more in this box and therefore you poured more, or you had less in this box and therefore you poured less. That's the dependent situation. But what really happens is they're independent of each other. The amount above or below the mean here doesn't affect the amount above or below the mean here, and therefore what you have is variation and more variation even though we subtracted. So this ends up with more variation than either of the other ones because we have randomness and more randomness. And that's why variances add together when you're subtracting random variables. And to me, that is the common sense reason why it makes sense that the variances add. The reason why it's variances adding and not standard deviations adding is complicated and you don't have to worry about it. But the fact that you get more variation when you take randomness and subtract more randomness, you get more variation. So that's that piece. And then I would like to do an example with normal distributions, kind of like these, but let's do a different example than the cereal. Let's do cups and lids. So cups and lids. You grab a cup, you grab a lid, you hope that the lid fits on the cup. It might not. They try to make it so they will always fit, but sometimes you get one that's too big or too small. So I'm just going to give you some data. The mean for the cups is 3.96 inches wide. Obviously, the manufacturing process is not perfect, and so there's a little bit of a variation in the cups, which is 0.01 inches. It's so close to being exactly right. And so we've got this normal curve. Oh, that's not a very good normal curve, sorry. That has 3.96 in the middle and 3.97 and 3.95, and we could add more numbers if we wanted, right? Lids, totally different distribution. The mean of the lids is 3.98 because you want the lid to be a tiny bit bigger than the cup so that it fits, right? And there's a little bit of variation here also, not very much. It's only 0.02, so that's not so bad. And we could draw another normal curve and we could label it as 3.98 and then add 0.02 is 4 and subtract 0.02 is 3.96. And as you might have guessed, some of these will not fit on some of these and some of them will. We hope that most of them will fit. All right, so a little further information for the lid to fit. We have to have the lid slightly bigger than the cup. So lid has to be bigger than the cup, and we can't have it too much bigger than the cup because if it's too much bigger, it just falls off. And so the lid minus the cup has to be less than 0.06 because if it's more than 0.06, it falls off. We could rewrite this as lid minus cup is greater than 0. So the lid minus the cup has to be between 0 and 0.06 in order for it to fit. If it's any less than 0, I can't get it on because it's smaller than the cup. If it's any more than 0.06 difference, then it falls off. And I'm going to grab a random cup and a random lid and hope that it works I want to know the probability that my random cup and my random lid will work together. Find the probability. That the lid fits. A random lid fits a random cup that I have just chosen off the stack of cups. That would be the probability that this happens, that 0 is less than lid minus cup is less than 0.06. That's what I'm about to find. So in order to do that, I have to think about this. Let's talk about the distribution of my new random variable, which is L minus C. The difference between the lid and the cup is my new random variable. Notice that it came from subtracting two random variables that are independent. So let's talk about shape, center, spread. I didn't put this in the ice cream and cake because it's kind of just a common sense thing, although in grad school I had to prove it. The shape, if you have two normal distributions and you subtract them or add them or do anything else to them, you're going to get normal. You're going to get an approximately normal distribution with a different mean and standard deviation than you had before, but the shape is not going to change because I subtracted them. And we're not going to prove that in this class. We're just going to say, oh yeah, it seems like it ought to be normal. Okay. Center, okay, we just learned this, right? Center, if I subtract two random variables, I can subtract their means to get the new mean. So the center, or the expected value of this difference between the lid and the cup, is just subtract the two means. It's mu L minus C is mu L minus mu C, which is 3.98 minus 3.96. Or in other words, I expect them to be about 0.02 apart. 0.02 inches, okay? So that's not a very hard calculation, but you might not have known before that you could do that. Spread is even more complicated because I'm talking about the standard deviation of L minus C, and I'm going back up here to my formulas, and I say the standard deviation of a difference of two random variables. That's when I do the Pythagorean theorem thing. I told you on one of my walkthrough slides or videos, I will be reminding you of this all year long. I'll say, oh yeah, remember it's the Pythagorean theorem thing. That's what we're doing. So we're going to take, I'll write the formula first. We're going to take the mean or the standard deviation of L and square it, standard deviation of C and square it, and add them together and square root. And now that you know that that's the formula, no problem, right? So I'm going to take this number, 0.02 squared, plus this number, 0.01 squared, square root the whole deal. And I get the standard deviation of about 0.02236, and I'll just put a bunch of digits to make sure I don't round too much. If I round too much, it looks like it just equals this 0.02, which it doesn't. It's not. It's a little bigger than 0.02. All right. So that is what we learned in the ice cream and cake thing that we haven't used for anything yet. But that's how you find the mean and the standard deviation of this new normal curve that is the distribution of this. So I could even make a new normal curve and say this has a mean of 0.02 and it has a standard deviation of a little bit bigger than that, which is crazy. So like this is a little bit less than 0 and this is a little bit more than 0.04. I guess I could do that. Nope, I put an extra 2 in there. I need my calculator, hang on. This happens in class all the time, that I leave my calculator across the room and I have to go get it. So you guys haven't seen me do that very often, because usually I remember before the video. So anyway, I'm going to do 0.02 minus that standard deviation I just got, because I want to know what that thing should be labeled. It is negative 0.00236, which means 0 is about right here, and 0.06 is way over here. So it looks like I'm more likely to have one that just won't fit on than one that falls off. They probably want it to be that way because one that falls off is really bad for the customer. If it just doesn't fit, the customer is going to grab a different one, and that will be fine. All right, so back to my problem. I'm trying to find the probability that 0 is less than L minus C is less than 0.06. And I'm going to find z-scores for both of these things. and do a normal CDF. This should sound familiar to you. You've done it before. The new part was calculating these. All right, so Z for 0 is 0 minus my mean of 0.02 divided by my standard deviation of 0.02236. I'm going to keep a lot of decimals because I feel like that'll make it more accurate with these itty bitty numbers. This Z is 0.06 minus 0.02 over that standard deviation. So when I calculate that, I get negative 0.89. I feel like I could round at this point and that would be fine. And this Z is 1.79. And I need to know the probability that Z is between those two values. So let's come over here and I'm going to find the probability that Z is between negative 0.89 and 1.79. And I'm going to look them up on the table or use normal CDF. So remember, I could look them up by doing negative 0.89 and get that number. And then I could look at the other side and get 1.79 and get that number and subtract them. Or I could do normal CDF on my calculator, which is my preferred way. Plug in the two Z-scores. In case you forgot, that's in second bars. Normal CDF, negative 0.89 and 1.79, and paste. And I got 77.65% chance that the lid will fit. We could also find the probability of the lid not going on at all and the probability of the lid being so big it falls off. We're not going to do that right now, but there's an example of what you would use those formulas for. If you're given a situation with two normal curves and you're given the information for each one separately, you can combine them. That's why it's called combining, to get the new center and spread and set up a probability problem like that. So that is lesson 6.2c. There will be a problem similar to this on the test. There should also be some in the review homework, I hope. I think that's all I have to say. There is a quiz on Friday, and then we have break. That's amazing. Woohoo! See you later.